What I thought I would do today is share with you what I'm doing at UT, the class I teach. It's a class that's not taught in any nuclear engineering program until now, and how that came to be. And then I'll talk a little bit about where Vogtle, or what we're doing with Vogtle, Natrium, and the versatile test reactor, and some other projects we're working on the nuclear side of things as Bechtel's chief. It certainly keeps me busy, and but I've enjoyed the opportunities. I've truly had a blessed career, and it's I'm very fortunate to be able to help the young people coming up through school. I will tell you that teaching class and then hiring some of my students keeps me out of the bad list on rateyourprofessor.com. You know, kids can go in there and say, who's got the goods on the professor? And I look every now and then to see if somebody said something, but you know, when you have the opportunity to hire some of them, it certainly helps your ratings. So let me see if I can share my screen. For those that you don't know me, I've got 40 years in nuclear business, all kinds of different jobs. Reactor operator at Hatch, shift supervisor there, reactor test engineer at Newport News Shipyard, 25 years as the chief of nuclear safety at Department of Energy was my last job, and I had some other ones prior to that. I was AECOM's chief nuclear officer, and then got hired by Bechtel a few years back, and came to Reston, and it got me within 10 minutes of my granddaughter. So I'm up here in Northern Virginia with family, so it's all been good. I'm with Bechtel. There's 4 divisions to Bechtel. The nuclear security and environmental side, that's the division that has the Pantex and Y-12 contract. We've also got Lawrence Livermore. We're building WTP and Vogtle from this section. There's also an energy section, which does pipelines, refineries, and oil and gas. There's mining and minerals, and big operations in South America and a few other places. And then we have our infrastructure projects. So I'm the chief nuclear engineer, the only chief that they have in nuclear. So anything comes up in the other organizations for nuclear, I handle from that. Bechtel's got a very deep value system. They've been a privately held company for 120 years. You know, and out in industry, there's Bechtel's way, the right way, and the wrong way. And they just have a way of doing things. What I've learned the hard way is they're not going to change. But at the end of the day, they do try to do the right things and try to do quality product in their engineering designs and plant construction. For nuclear builds across the country, they built 80% of the existing nuclear fleet. It's pretty amazing. They built Hatch where I worked before. They built Turkey Point. So I've had a long career association with Bechtel. So it's, in some ways, it's nice to be working for them again, and so forth. So for our national nuclear security operations, we have Livermore, Pantex Y-12, UPF, which is under construction there, and Bechtel plant machinery for the naval marine propulsion. With nuclear power, we have the versatile test reactor design and development, Vogtle 3 and 4 construction completion, Hinkley Point C, where we have project managers on board there for that project. Southern Company, we still support their existing fleet, Farley, Hatch, and Vogtle. We've got some shielding work that came in today, as a matter of fact, and we're going to be redoing their in leakage for the Hatch control room calculations. We'll be redoing those here in the coming months. Natrium, we've been teamed with TerraPower to design an advanced reactor. Natrium, it's a sodium fast reactor, interesting design. And we're working through that as we speak. The Poland nuclear feed study is a study to look at the Polish environment for regulation, and with the opportunity to build 6 AP1000s there in Poland. So we're doing all the site characterization work, all the licensing work, and the studies necessary for them to make a decision on whether or not they want to proceed with 2, I think it's 2 sites with 3 1,000 megawatt AP1000s at the sites. We have the defense and space projects, Pueblo, Bluegrass. Just last week, we finished all the destruction of all the mustard gas weapons in our arsenal. So those 2 plants are making great progress. Pearl Harbor infrastructure optimization. We're designing the new dry docks and helping them modernize their ship repair facility out at Pearl Harbor. Ground-based strategic deterrent. We're designing some new missile silos for that project. And then we got Mobile Launcher 2 down at Savannah, Cape Canaveral, excuse me. And then down below, we've got the waste treatment plant, Savannah River site liquid waste contract, and then the Sellafield pile fuel cladding retrieval project. We got quite a bit going on all over the world and working on more every day. One of the things I'm involved with is a Fukushima wastewater project to put another waste treatment facility at Fukushima to continue processing the reactor water that's coming out of the reactor buildings there at Fukushima and the ongoing cleanup activities. So when I came to Bechtel, my boss, they had worked out an agreement with between CNS and University of Tennessee, a cooperative agreement. And one of the subjects that came up was training people in a nuclear safety minor program, which would allow students to come out of college and have some understanding of how to do nuclear safety at DOE or commercial sites. And really what you find out when you start looking at the problem and you look at the curriculums that are going through the nuclear engineering programs, what is missed in all of these is that nothing happens without a license. Some sort of regulatory, okay, you can go do that, whether it's a DOE approval through a documented safety analysis, or whether it's the NRC through a formal license process. That's true for medical facilities, fuel handling facilities, reactors, research reactors, all those kinds of things. Somebody's got to say, yeah, safety's good, we can move forward. So I developed this course, I wrote it, and it's really an introduction to the business of nuclear and the role of regulation. Because really, when you come out of a nuclear engineering degree, if you're going to go nuclear, you're either going to go work in the commercial power sector, you're going to go work in the DOE side, or the government side. Those are really the 3 flow paths you have. And I try to make students aware of what those options are and what kinds of jobs are out there for those kinds of things. We cover both DOE and NRC regulation. We cover the big ones, 10 CFR 50, 52, 55 with respect to reactor operator licenses. We cover DOE orders and policies and standards. Between the 2 courses, I'll take a break and we'll do some accidents. We'll look at Fukushima, we'll look at Chernobyl, we look at TMI, and then we discuss what their impacts on regulations was and how that evolved. One of the things that's not lost on me here, which I try to impart to the students, is that I came up in the reactors in the 1980s. So everything we did, whether it was training at Newport News, training at Georgia Power, we covered everything from soup to nuts on what happened with TMI. And you know how the regulations changed from 79 to 90. Some of it you can say created the job or the opening for me to go to Hatch. One example is the desire to have degreed engineers on shift. And so fortunately for me at that time, I was interested in running a commercial plant and had that opportunity. Then we go through some practical application of regulation to real situations. This is where I have the students really take a look at some of their research projects. Some of them are working on micro reactor designs. Others are working on modeling. Others might be working on accident tolerant fuels. And we take a look at those situations and, okay, if you're going to go implement your research, how do you go about doing that at either a commercial plant or a DOE site? And how do you evaluate, 10 CFR 5059? How do you do change analysis and those kinds of things to bring your research to fruition? And so what regulations do you have to meet? And how do you document those? So they have to write a paper that governs how that works and how they would go about doing that. And then the last thing I try to help the students with is their career path. Working both sides, the NRC and the DOE side, there's not much I haven't seen. Been, very fortunate to do what I've done. And I like to share that with them and help them figure out what it is they might like doing when they graduate and get out in the industry. So that's what I've tried to do with the course. It is an elective course. I teach it on Monday nights after my daytime job. I teach from 6 to almost 9 o'clock, and it's been working. I think it's worked well. The students seem to enjoy it, and it's been fun for me. So here's an overview of the course elements, NRC regulations, and then root cause analysis. I actually go through the different aspects of root cause analysis. At one time in my career, I ran the accident investigation program for DOE. And some of you in Oak Ridge maybe remember the NAC explosion in 1999. And out there at Y12, I was part of that accident investigation board. I'm sure Donna remembers it. And then we talk about what those accidents impacts have. I will tell you that Fukushima and Chernobyl are as much of a culture problem as they are a nuclear safety problem, and why we have safety culture at DOE and NRC sites. Then I get into the DOE rules and orders, safety analysis, and then go through project presentations and final exam. If you stacked up all the regulations over the years that we've all had to come know and love, for better or worse, there's an excess of 4,000 or 5,000 pages of regulations out there. And I don't try to get them to understand it all. I want them to I want them to know where to look and know when to ask for help. And so it really opens their eyes. There's a lot of reading involved with this and trying to get them into multiple places on, in DOE and NRC space to understand where it's going. So when I talk about, this is a little bit of a dated slide, but it's as close as I can come to going down your different career paths. On the top side, on the yellow brick road, is a commercial no pun intended there, but it's a commercial mode of operation, if you will, with uranium enrichment, fuel fabrication, and commercial operation of power production facilities to produce electricity. On the blue road is your DOE side, enrichment, fuel fabrication, production, chemical separation, and then, excuse me, weapons fabrication and dismantlement, and then nuclear weapons production. And in between both, you have the waste issues with both of them and what you do to dispose of waste. So that's where we try to put things in perspective and talk about relationships. And so people understand, you know, what the different organizations are doing for each other or not, and so forth. This is a chart I confront them with on day one. This comes out of the Livermore National Lab website, which I really like. There's a lot more detail on this chart, but basically it presents the energy problem that we have in this country. And I try to get the students to think broadly about the role of nuclear, the role of solar, hydro, and the other contributors to the energy grid. And one of the problems they have to start out with is if you wanted to replace, for example, coal with 9.21 quads of energy produced every year with nuclear, and you just took a straight conversion, there's approximately 100 nuclear plants currently operating. I think we're a couple under that right now. But to produce 9.21, you're looking at another 120 reactors just to replace the coal production, electrical production in this country. Okay. If you look at replacing, you know, your transportation sector with batteries, okay, you got to get up to 30.2 quads of energy. This is 10 times 15 BTUs. You need probably about 450 nuclear plants. So then I have them go through and calculate how much square footage do each of those take for a solar, and how much windmills would take to use wind. And if you factor in the capacity factors of both, wind being about 17% and solar being somewhere around 23%, it requires quite a huge development to replace this balance. So when you look at that, it's quite telling about the energy situation. I think last week the president announced he wants to give $45 billion to solar. Somebody needs to go ask him how many kilowatts per dollar are you going to really get out of that? Because it's going to take quite a bit to do. To make any dent in this equation and the balance we have right now, it's going to take a huge investment. It can't be one or two here and there. It's just not going to help. So it's a very telling slide. There's a lot more information you can get out of it. One's rejected energy, how much of energy we produce is wasted due to the limitations on the thermodynamic cycles. So it's just something I try to make them realize the problems that they're going to face in their careers and get them to think a little bit about the bit broader picture. So one of the things I look at in terms of errors, if you look at the history of nuclear, you really had the discovery period from 45 to 74. And this is the time frame where we ramped up the size of reactors, tried some different types, and really understood what it took to regulate. And it's led to the separation of the AEC into the Department of Energy. And then you have your regulatory period where you're establishing, the NRC is really establishing what it's about. And when it became a commission in 74, and then you get into your reactor safety period. And then I call the last period since 2005 economic survival and the outflow. I think we're at the dawn of a new era if we can get Natrium done as scheduled in 7 years. I try to look at this as the first step, and hopefully we'll see some more being ordered and built in the near future. This is a demonstration project. I'll talk a little bit more about how this plan is arranged and why, and how much of this is regulatory driven. It's quite interesting how this has been developed by TerraPower. Any questions on the classwork? Okay, I'm going to move forward into Natrium. Natrium is a demonstration fast reactor using sodium as a coolant. It will be NRC licensed, and it benefits, it's designed to cost. It's supposed to be a simple design, rapid construction. We're looking at using some different techniques to build a facility with pre-constructed shield walls, using steel composite construction. And we're going to complete the design prior to commencing build. It's going to have a 41% net thermal efficiency, which is relatively high. You think about the heat rejection on the previous slide. Integrates with renewables through molten salt storage. There's 2 large salt tanks that will hold hot salt that can continue to produce power after a reactor shutdown for some period of time. Right now they're claiming 5.5 hours, but they're thinking they can get more out of that. Load follower with 24/7 operations at 100% power. So it's a single unit site. What you're going to see here is a reactor building, which is your spent fuel is in the fuel building next door. Your reactor, your fuel auxiliary building, this is where you bring fuel in and out. Reactor auxiliary building is over here. And then your shutdown cooling is air system and ventilation. So that's right here. The salt piping goes out the back, goes to the steam generation facility. And then you have energy storage tanks. This is hot sodium. This is a secondary loop of sodium. It's not the primary loop. So in theory, it's not contaminated. And this fence line is your QA control line. Okay, so this is all nuclear grade QA1 and NQA1 design specs and everything related to this part of the island design. Everything here is industry acquired and procured standard industry practices for this part, for your steam generation and your cooling systems and so forth. Fire water tanks and standby diesels in your warehouse and administration. So your control room sits over here. Control building sits over here. And then your control distribution center is over here, nuclear instrumentation and controls.
Is it currently being built?
No, it's in the design stage. We're 6 months into the design stage.
And what's the date for starting operation?
2027.
2027.
27.
Okay. Thank you.
So normal operation, you got a hot core, sodium coolant around it. Your sodium pumps are on either side circulating. Air is flowing on the outside. Everything's contained within the vessel. And your sodium loops come out of the top, and it's operating at atmospheric pressure. Okay. Utilizes a fast neutron spectrum. Pretty much operates the same way a thermal reactor does. Some of your controls are a little different, but by and large, it's the same operating principles as a thermal reactor. You're just using the fast neutrons in the spectrum. Highly subcooled. Not only do you have your core, you're surrounded with primary sodium and then your secondary sodium loops. Okay, the control rod drives operate fairly similar to what's currently designed. Highly reliable shutdown system. Intermediate heat transport. So nothing touches the primary. And this is done internally here. This is the pipe that goes out to the island behind for the steam production. And this is a large thermal inertia. Okay, so you have a long time before emergency cooling or other issues arise and a loss of power, and the thing just sits there. It will cool itself and not melt down. Utilizes pump coast down as part of the control scheme post-accident or post-loss of offsite power control scheme. Everything's self-contained. I think the problem we're going to have with licensing, when I look at how we're going to license this thing, is convincing people that accidents are not a significant risk contributor, and that it can be operated the way it's designed. You're looking at a site boundary and an emergency planning zone of the fence around the facility, with the idea being you have no public evacuations or so forth. Everything's contained within the site boundary. So we haven't gotten into the reactor accident analysis. We've got the old stuff from fast flux test facility, and we're building on that, running the codes and starting to look at the results to confirm we can meet those commitments. So we have passive heat removal through the salt for accidents, no reactor vessel penetrations, and resistance to software common cause failure. This is a Natrium thing. I haven't seen how they declare this, but we'll be getting into it when we get into licensing, I'm sure. Gravity-driven control rods and standby rods. Negative feedback with increasing power or temperature. Even with no control rod drives, it will shut itself down. There's a passive safety-related reactor vessel air cooling, and there's also passive non-safety air cooling via intermediate air coolers. And that's the intermediate stuff is coming in around the vessel. And the thermal inertia will cause continuous flow through the vessel, completing the cool down. It's a passive confinement. It's not a containment. And so there's no penetrations in the primary vessel. There's a guard vessel that prevents loss of coolant. And any accident, if you did have something go wrong, a QA failure in a fuel element, the sodium absorbs the fission product. So we're going to switch over to Vogtle Units 3 and 4 completion project. Bechtel was the fourth architect engineer in on this project. This is a look at Unit 3's turbine deck, and the overall construction. Unit 3 is here below, and Unit 4 is coming along behind it at the Vogtle site there in outside of Augusta, Georgia. It's two AP1000s, both rated at 1,117 megawatts. AP1000 operates on gravity and neutral circulation for core cooling, even in the absence of operator intervention or mechanical assistance. First units built in the United States. And then we're working for Southern, and that's an ongoing project. And we've come in there and taken over engineering, and we're going to get it to completion now. So it's just been, COVID's actually hit the plant pretty hard early last year, and they've managed to work through it with lots of changes in how they do things. The regulatory aspect of this is 10 CFR 5052, which was a combined operation and construction license. And if you ask Southern if they would do that again, they said no way. They would go back to the old Part 50 methodology because the follow-up with the items important to safety and the ITAC process that's used to confirm that the operating license is being met has been more intrusive and cumbersome than they ever thought would be. So Natrium will be a Part 50 license application, and we'll see how that goes. Here's the AP1000 layout. 2 steam generators, reactor, pressurizer in the primary containment. What you'll see in the other drawing, how the containment looks different from the Vogtle Units 1 and 2, because you have these huge water tanks up here for cooling and so forth. And that's your passive cooling containment water tank. Okay, so you have an inner dome and your outer containment, and everything else is pretty much standard BWR. So when you look at this, here's Vogel's Unit 1 and 2. I worked at Vogtle Unit 1 for a month when they started up the first year operation, 1987. They ran for about a year. I had 27 trips. So I went up from hatch at the time and did the root cause analysis and the 27 trips that Vogtle Unit 1 experienced that first year operation. So you see the little difference in containment design with the water tanks situated on top of the Unit 3 and 4. This is what the conceptual design of what the site will look like when all the construction is complete. Again, 2 cooling towers, 1 for each, and then so that's what the site will look like. Lessons learned. What you learned in 90% design for a license application doesn't mean design's complete so you can go build a facility. We've had to go back and redo quite a few things, and it's set us back a little bit. Underground work first, go figure that. We learned that in the DOE in the hard way when we did some design build activities, and then the seismic capacity of the structure was challenged, and we had to go back and dig some holes and characterize the soil structure underneath the facilities to make sure it was going to meet all seismic capacity needs of the design. Steel composite designs, we've managed to do some of that work initially with this project and know that it works. What that means is the steel walls come in and they serve not only as the structural part, and all the penetrations are done in the shop, but then you load this wall in and then you fill it with concrete. So it also serves as the shielding capacity as well. So we managed to do that in the reactor auxiliary building and some of the other things. And then we're working on assure the overall layout of the facility meets the mission requirements. We had some interface problems with some of the vendor skids coming in and had to rearrange those. Layout of temporary construction facilities. You need a good area to do that and then maintain your NQA1 status on a lot of the equipment that comes in, specifically if you get into delays. Virtual design and construction, because there had been so many engineering organizations in there, we were not able to contain it into a model that you can design and build to. So we're using the old-fashioned methods and finishing it the hard way. So those are the things we're factoring all these into the AP 1000 feed study for Poland. We've got volumes of lessons learned on how we do this. If we don't get that one going, I hope we don't lose the capability. Versatile test reactor. Right now, this reactor is up in question. It looks like its funds have been zeroed out, but there's some rumors that they may get some limited funding to keep the design going. But it's a 300 megawatt sodium fast cooled reactor to provide testing capability out at Idaho for fast neutrons and high temperature environment. It's pretty much a very similar design to Natrium. It's going to use the same essential design. The one difference will be VTR will be entirely air cooled and not used for any power production. So we're waiting to see how this plays out. But it was going to really originally plan to be the test bed for some of the components that went into Natrium. So they've had to go back and reevaluate how they're going to test some of the components that aren't going to go through VTR now as a result of they getting zero funding. We are going to transfer. We have 15 engineers working on it now. By October 1, they will all transfer over to Natrium and continue the fast reactor design work that we're doing for that. So that's the end of my talk. I'm opening up the floor for questions. And again, thank you very much for the opportunity to talk about what we're doing. It keeps me busy and keeps me working all the time.
If I might stick myself in here and mention one question that came in on the chat earlier. It was a question about how many people do you have in the nuclear engineering class that you talked about? Okay,
I have 20 students this year. I have 12 graduate students and 8 undergraduates. And it's grown. The initial class was 8. Last year, I believe it was 15. And this year it's 20. Any other questions?
Yeah, I have a question on your very interesting graph about the US energy. On the extreme right, there is a figure, and I don't know if it's unit of something or percentage, 60 for wasted energy and 30 for used. Is that the normal breakout of how we dispose of energy? have to eliminate 60% of it.
That's the number. It
Interesting.
varies by plant and the amount of, combined cycle gas turbines will get about 40% energy production and 60% rejection. I think most of your commercial reactors, because they're not able to superheat, are running in the lower 30s as a matter of energy production versus, 65 to 70% heat rejection.
Yeah, it's interesting, your comment that it will need 100 nuclear plants to replace coal and 400 to replace petroleum. This
Mhm.
is quite a sobering thought.
Yeah,
So you
it is
still
quite sobering.
stand by those figures in rough value?
Yes, I do.
Yeah. You've been in this business a long time. So where is the biggest hope in the future? You have not even alluded to the fusion. And we had a discussion not too long ago that it has been eternally 20 years ahead of us. And but we are still making progress. What's your take on fusion?
Fusion, in my mind, needs a lot more money invested in it to make it work. The slow pace of ITER and getting that going has not helped, I don't think. And I think I think it has a lot of promise, but we've got to get serious about the investment.
So curiously, that's about the thought about why we did not win in Afghanistan, because we did not put enough money there.
Could I ask a question about the interaction between the sodium, the hot sodium, and the surface of the container holding the sodium through the reactor? What kind of material are you using to contain the sodium?
I believe the vessel is all stainless steel.
And what lifetime can you give to the stainless steel before you have a problem containing the sodium?
Design life of the plant is 40 years.
So the stainless steel holds up pretty well against the sodium?
Yeah, we had enough data from FFTF to make that assertion, yes.
And is there any place where the container is separating water from sodium?
You do that in the refueling floor. There's a wash station for when you remove spent fuel out of the vessel. You insert it in this container and you do a steam spray initially for the initial reaction, and then you would do the washdown. So there's going to be washdown stations established because sodium reacts very violently with water.
Yeah.
Yes, I'm very much aware of that.
Thank you.
I give the lessons learned on sodium interactions from the NAC explosion at White 12.
Atomics International back in the 60s, late 60s, was very, effort was very great to develop the sodium loop.
Mhm.
And what type of materials efforts have been used to ensure that there will be no issues with regard to material degradation over that 40 years?
Well, I don't know what Natrium has in store for that yet, but I'm sure there's going to be some surveillance requirements to address those issues built into the process. We're not there yet. we're doing initial designs right now, so I haven't gotten into that. But
Thank you.
Another question that came in was how many nuclear plants are closing annually these days?
well, San Onofre is the first one that's due next year. We're hoping that gets delayed. California has no grid left from what they've done to their power plants, and we'll see if that continues. There's the other ones in Illinois, which are looks like they're going to get some subsidies, but for minimal investment, you're going to get a lot of megawatts. So I don't see why they wouldn't do that, particularly when you're looking at this graphic I had. So I'm waiting to see how that plays out. But all the rest of them are undergoing, there's been several that have extended their licenses to 80 years, and I look for more to do the same.
I have a question on the funding and what your guess is what's realistically going to happen over the next 20 years. If they're saying by 1930, the vehicles are going to go electric, but at the same time, TVA's trying to figure out how to pay for getting rid of their coal ash at their existing plants that they're shutting down. And their demand is not expected. Well, I don't know. I guess that's the question. Is the demand going to go up or down? They're not necessarily expecting enough increase in demand to justify huge capital investments. I mean, it seems like there's just going to be a big crunch coming. And what's your guess as to what's going to actually happen in the next 10 or 20 years?
Well, I think, you know, I'm sure it's politically correct to say we're going to go do more solar, or we're going to go make all our cars electric. The reality is it's not feasible. And I think Toyota came out and recognized, and they've been behind the scenes lobbying, saying, we're not going to commit to that because, you know, it's not a reality that we see happen. I do think they're going to continue to encourage people to go to electric vehicles, and as that demand increases, it's going to put a strain on the power grid, and then some things will have to change. But I see some more events like what happened in Texas with the blackouts and things happening before something changes. We got to hurt people emotionally before you can get them to take action that means anything. Unfortunately, that's the way we are as human, in our human nature, but that's what I see happening. The fortunate thing about electric vehicles, if you look at the thing you don't see here is what the energy consumption during a typical day. And it usually peaks around 3 or 4 o'clock in the afternoon, particularly in the summer when people are trying to cool their homes, is when you get the largest peak out of the cycle of a day throughout the year. And then when you get to people plugging in their cars at night, it helps balance the demand on the grid, which would make the case for more nuclear providing a base load. Because, you know, solar is available during the day. Hydro is really a load flattening operation more than it is a power production. And then wind is has a 17% capacity. And you can't store this. So where do you get the balance on the grid? And that's what the utilities are constantly struggling with.
You alluded to Pacific Power, but in our own neighborhood with TVA, I mean, they've been talking for, I don't know, I guess 4 or 5 years now about trying to get the modular demonstration reactor at the Clinch River site going, and it doesn't seem like much progress is being made there. What do you think TVA is actually going to be able to do in the next 10 or 20 years in terms of new facilities?
We've been able to patchwork everything and keep things as is. So what's going to create the sense of urgency? And I don't know what that is. And I don't know, I really have my reservations whether or not we're going to get Natrium through a licensing process that's not very well defined right now for a fast reactor. I see some things, I have a strategy. We're working with Natrium to get that through, but it's going to be an uphill climb. But I don't see anybody having that sense of urgency or that vision that says, this is a crisis, you know.
And what is the capacity of the US industry to actually build nuclear power plants?
And that's true for electricity or electrical plants. That's true for batteries. That's true for solar panels and so forth. You can just go down the line industrial and what are we ready to handle? That's why I don't see this changing very much until that sense of urgency gets cooked into a national agenda. And a lot of people are never going to understand this.
One of the things that was mentioned regarding the modular reactors was that the NRC doesn't really have staffing to consider anything new and different. Do you expect that's going to also be an issue relative to your sodium reactors?
Oh, yes. And I look at half of what we have to do as part of the licensing process is train them in the design, train them in the acceptability of the design, and then go through iterations of questions. So I look at more, and what I'm promoting is more frequent and off interactions with them, going through system by system, general design criteria by GDC. How are we meeting this? What standards are we using? And just mapping that out until there's nothing left to map. Because I think we're going to have to take each GDC, even though it's for light water reactors, and show or demonstrate how an advanced reactor will meet that or not meet that, and then give them 5 reasons why in every situation.
If I understand right, a lot of planning and on all the horizon is needed to solve this problem. Do you agree?
Mm-hmm.
And of course, it's encouraging to see that you're introducing at the university a course to make new engineers interested in nuclear aware of all the various problems they will face. That's good.
Okay.
On the military side, what is happening in terms of development, or is there any need for much change? And also with regard to space travel, you know, out of the galaxy, or at least within the galaxy, is there any research going on? What kind of reactors could be used for that?
I'm not as, I can't speak on the space travel kinds of things. There's all kinds of designs out there, and theoretically, you know, a reactor is probably a good thing in space. The carrier, the latest carrier, the Gerald R. Ford, is the newest reactor design that made the fleet in the United States Navy. It is, it's a more streamlined design over the previous versions on the Nimitz. If you remember, the the Enterprise had 8 reactor plants, which was reduced down to 2 larger reactor plants on the Nimitz design. And then the evolution of that has gone to the Gerald R. Ford, which is a basic, it's a reactor, steam generators, and a steam cycle that goes only to the main turbine and the main generator. And the generator and the main turbines share a common condenser. So it's a once-through steam cycle. There's no steam-driven feed pumps. There's no steam-driven catapults to launch the aircraft. There's no steam in the engine room anywhere other than what goes to the turbine. So they reduced, the idea behind this was to reduce maintenance costs and reduce staffing levels in the engine room. So it's a more, it's a simpler design in one way. It's more complicated in that everything's electronically controlled. And, but from a steam plant side, it's the next evolution of what the Navy felt like they needed for carrier missions in the future.
And how about the submarines?
Submarines are pretty much evolutionary designs. You see little incremental changes between different additions to plants, but nothing significant like this. SAG, I think, is the latest version of that on the latest submarines.
Maybe I missed it before when you said it, but how much smaller is the overall size of the plant with the Natrium reactor, and does it use the fuel more efficiently?
Burnout numbers burnout numbers I haven't looked at. I do think it's more efficient. You don't have the with a fast reactor design, you don't have the long-lived nuclides present in the waste. So I do think it's more efficient thermally with respect to neutron usage and fuel usage. Footprint size, it's a lot smaller. The building is a lot smaller, but actual square footage, I couldn't tell you. It seems like a lot simpler construction and operation will be. Because you don't have all these redundant safety systems.
Right. Well, I do notice that it's now 1 o'clock, which is our scheduled end time. And it may be that you're willing to stay on and answer some more questions if people have them. But if we don't have any more, and I guess maybe I'll take this opportunity to let people think about that. I do want to thank you so much for talking with us today. You know, I don't think there's any substitute for people who have long practical experience in a field to get a broad view of what we think the issues are. It's easy for people to do theory and academia, and that's also very useful. But somebody who's got all this experience, I think, is invaluable. And I want to thank you so much for talking with us today.
I enjoyed it.